David here. Welcome to the channel. Today's all about symmetry in systems. This is chapter 7 of the book, The Science of Systems. If you want to learn more about the book, you can go to davidsugar.com/book. There you can download a free PDF of the book. Additionally, you can buy the paperback version on amazon.com. There you can see all the images we're going to review here in person. So what is a symmetry in a system? A system here, reflected with the term S, has a symmetry when it follows the equation that a given quantity X is mapped back to itself. So a symmetrical mapping is a mapping which brings a given object back to itself. For example, if we look at an equilateral triangle, if you rotate an equilateral triangle by 1/3 turn, it looks exactly the same as it initially was. This can be thought about as a symmetrical mapping, a mapping which preserves the structure and maps the initial object back to itself. One of the most common types of symmetries seen in nature are circular symmetries. Now, nature is, three-dimensional, so we don't actually see flat circles. But if you slice various objects and look at a silhouette, then you often see these circular patterns. And these are approximate circles. And a circle has a symmetry that no matter how many angles it's rotated, like 1 degree, 2 degree, 3 degree, it will look similar or look the same as it initially was. Now, these are approximate circular symmetries, not perfectly. But one example is the circular outline of a moon. So the moon is approximately a sphere, and the silhouette of the moon is a circle as seen from Earth. Additionally, if you slice an onion in half, you see these near circular rings. They're not perfect, but they're approximately circular, where if you rotate the onion by a certain angle, it will look identical. Additionally, there's various circular rings in a beet slice when you slice it. Now, a circular symmetry can also be thought about as different fold symmetries. And this is, instead of saying a continuous symmetry around a circle, this is just saying there are some discrete symmetries. So one is a twofold symmetry, where basically if you rotate the object 1/2, 1/2, then the object will repeat, like this circle with a line in it. Threefold symmetry means that the object repeats when you rotate it by 1/3. Fourfold is 1/4, similar to like a square. Fivefold is 1/5 turn, similar to a pentagon. And sixfold is 1/6, similar to a hexagon. Now, interestingly, these can be thought about as subgroups, subsymmetries of a circular symmetry, all continuous rotations. These are just saying there are certain subsets of those which are allowed: twofold, threefold, fourfold, and so on. Now, there are common fold symmetries seen in nature. One type is a bilateral symmetry. Now, bilateral symmetry means that the object looks the same when the image is flipped left to right. So for example, this shows this image of this crab where the feet and the legs are near identical if the left side of the image was flipped with the right side of the image. Now, there's also different fold symmetry in flowers through different rotations. So there's like 3-leaf clovers, for example. This is showing a 4-leaf flower. So it's approximately symmetrical. When you rotate it by 1/4 of the turn, the pattern will look the same as the initial condition. There's also 6-fold symmetry seen in snowflake. So there's a lot of these different fold symmetries seen in nature, as well as bilateral symmetry. And even, vertebrates like humans have a near bilateral symmetry where the arms on the left and the right side look almost identical to the arms and the legs on the right side. Now, another kind of symmetry which can be seen is when circles are packed together. So this is working to bring circles as close to one another as possible, as close to a center point. When you have one circle, this creates one circle. When you have two circles, you push them together. They are arranged in a linear format. Now, when you have 3 circles, you push them as close together where they're not overlapping, circles of the same size. This will create an equilateral triangle. This is the most efficient way to pack it. 4 circles creates this square. Now, 5 circles has numerous arrangements, and this shows a pentagon packing. So each one is each of the circles has a circular arrangement around the center point. And 6 circles are here packed together in a circular arrangement, creates a hexagon pattern. Now, these are also equivalent to the polygons because each of the radius of the circles are the same, and similarly, each of the polygons have equal edge lengths. So these circle arrangements of circles creates the polygons. Now, interestingly, 6 circles in a hexagon has just enough room for a 7th circle to fit inside of it. So it's a very unique packing. And once a 7th circle is packed inside of it, you can see that this also creates lots of little triangles. And this triangular packing or a hexagonal packing with circles in the middle of them is the most efficient packing of circles on a plane. Now, want to give an intro to some tilings. Now, we saw earlier those different circle packings can also correlate to triangles, squares, hexagons. And if we extend that out, we can pack circles on a plane. So one example, this is just showing the edges of the polygons, but the circles can also be reflected on the vertexes of each of these polygons. A triangular packing is packing together different triangles. Square packing together different squares. And hexagon packing together different hexagons. Now, triangular, square, and hexagons are the only regular packings of polygons. This means that they regularly repeat and that there's no other shapes. So it's just purely triangles or purely squares, purely hexagons, and it fills an entire plane and it regularly repeats. Interestingly, the pentagon cannot fill the plane. When you put 3 pentagons near each other, there's unavoidable empty spaces. So it's impossible to completely fill a volume with no empty gaps just with pentagons. There's always going to be these unavoidable empty spaces. Now, you can fill these empty spaces with other shapes, so there can be multiple shapes. You can create regular packings of pentagons with other kind of diamond shapes and other shapes. And you can also create aperiodic patterns. And now, aperiodic patterns are really cool. It can be shown that aperiodic patterns can fill a volume through substitution rules, where you basically substitute one element with many other elements and then continue to do that. So there's a proof that can be shown through a substitution rule that this aperiodic pattern can fill a plane. However, it doesn't periodically repeat. That's why it's called aperiodic. And so pentagons can also be arranged in aperiodic patterns, like this one shown here. Another really interesting type of circular packing that relates to the golden ratio is working to get as many circles together around a center point as possible. When you have a large number of circles, the optimal arrangement to have all the circles around a center point in a circular format uses the golden ratio. Now, the golden ratio is when the segment of A divided by B equals A plus B divided by A. Another way to think about this is that when the large part divided by the small part equals the ratio of the large part divided by the small part equals the ratio of the whole divided by the large part. Now, the golden ratio angle is taking this ratio in terms of an angular form. And you can see there's 2 angles, A and B, and these follow the golden ratio. Now, to create the circular packing we see here, it follows a very simple formula. Each number of circle rotates by the golden ratio angle, and the distance from the center is the square root of the number of that circle. So, for example, the 10th circle, the distance from the center is the square root of 10, and the 11th circle now rotates by the golden ratio angle, and now the distance is the square root of 11. The 12th circle is a square root of 12 from the center, and now it rotates by the golden ratio angle compared to the 11th. Now, this golden ratio angle is really interesting because basically it creates a scenario where it's an irrational number, the golden ratio, so there aren't ratios that repeat. So it never repeats. It's not like circles start to organize, around 1/3 turns or 1/4 turns or any ratio. It's irrational, so it fills in all these empty spaces. And there's some cool math to explain why the golden ratio is this optimal solution. But this often comes about in plants. So if there's a whole bunch of little near circular elements of a plant, like little flower pods, often seen in like sunflowers, as they naturally just stack around a center point, they would often create this golden ratio packing or approximations close to it. Additionally, if leaves are growing similar to a succulent, different petals, the golden ratio angle allows an opportunity to maximize sunlight collection. So if each leaf, is approximately growing the square root of the time since the beginning, using this golden ratio angle, make sure that each of those petals is not covered by another petal. It has maximal sunlight availability. So wanted to give some examples of this golden ratio packing. We see here there's some examples of the sunflower as well as the pine cone. Now there's also an interesting connection to the Fibonacci numbers. The Fibonacci numbers is a sequence created where each number equals the sum of the two previous numbers. So 1 equals 0 plus 1, 2 equals 1 plus 1, 3 equals 1 plus 2, 5 equals 2 plus 3, and so on and so on. The numbers continue to 8, 13, 21, 34, 55, and continue. Now, what's really interesting about the golden ratio circle packing we saw earlier is that if you look at the various clockwise or anti-clockwise spirals at any given point, like how many how many edges are kind of going off the circles, and they can be drawn with little arrows, these are always the Fibonacci numbers. So we see here with this sunflower example, there's 21 spirals, which is one of the Fibonacci numbers. We see here with this pinecone spiral, there's 13 spirals that come out Fibonacci numbers. So additionally, the ratio of two Fibonacci numbers approaches the golden ratio. So 21 divided by 13 is pretty close to the golden ratio. Like we said earlier, the golden ratio is irrational, so it can never be perfectly represented by a ratio, but the Fibonacci numbers present a close approximation. So this shows interesting connections between golden ratio packings, Fibonacci numbers, and patterns in nature. Wanted to now extend symmetry to 3 dimensions. So one interesting way to do this is to have a circle on a plane, but now extend it along a Z vertical axis. And this would create a cylinder. If that same process was done, but the circle was smaller as it was raised on the Z axis, this will create a cone. If that process was done, but now with a square base, this will create a square pyramid. 6 squares can also be volumetrically stacked together to create a cube. For a circle, you can also rotate a circle in its center point along another axis to create a sphere. Additionally, a circle can be rotated along another perpendicular circle, a larger one, to create a torus, also this donut shape. So these are common volumetric symmetrical patterns. A lot of these elements are used in like architecture. I also wanted to highlight the regular polyhedron. Now, these are 3-dimensional regular solids, also known as the Platonic solids. And they're created through the polygons, which are the 2-dimensional regular shapes. So we looked at this earlier, the regular triangle, the regular square, the regular pentagon. Now the tetrahedron is made with 4 equilateral triangles put together to make this 3-dimensional polyhedron. The cube or hexahedron is made with 6 squares. The octahedron is made with 8 triangles, icosahedron 20 triangles, and dodecahedron 12 pentagons. And now there's only 5 regular solids. Only 5 solids can be made with repeating the same 2-dimensional polygon. There's other solids like the Archimedes solids that mix different types of them. They could be different sizes. So there's an infinite amount of 3-dimensional polyhedron in general, but there's only 5 regular polyhedron in 3 dimensions that only use one type of polygon to be constructed. And now these are highly symmetrical shapes. They can be rotated along different axes to to get back to the original condition and show various types of rotation and also reflection symmetries. There's a lot of interesting connections between the various polyhedron. One of them is the duals. A dual of a polyhedron is when the points of one polyhedron touches the face of a center of another polyhedron. So the tetrahedron is its own dual. It's a self-dual, where if you take a tetrahedron, you rotate it by 180 degrees, now it can fit inside of a larger tetrahedron with the points touching the middle of the face of the larger tetrahedron. The octahedron and cube are duals of one another. This 6 faces of a cube can be touched by the 6 vertexes of an octahedron. Additionally, the 8 faces of an octahedron can be touched by the 8 vertexes of a cube. Furthermore, the dodecahedron and icosahedron are duals of one another. There's a lot of other interesting connections between these solids. One is to take an octahedron and to do a process called stellation, where you extend out the face. And if you extend out the face of each of the octahedrons, you kind of pull it out, as shown in this image, you would then create a star tetrahedron, 2 tetrahedrons that are intersecting one another. And this would create the map to the 8 vertexes of a cube. So you can see that the cube can also be thought of as constructed by 2 tetrahedrons in a star formation. Additionally, 5 cubes can define all the vertexes of a dodecahedron. So there's lots of interesting connections between all these solids and how they interrelate. We talked about circular packing, but now I want to extend to 3 dimensions to talk about spherical packing. And spheres are really interesting because they contain the largest volume for the smallest surface area. While a circle has the largest areas for the smallest boundary, a sphere can be thought about as a higher dimensional analogy of this circle. Now, similar to the circles, when you pack 2 spheres together as close as possible, they will create a linear arrangement. When you pack 3 spheres as close to one another, it also creates the same pattern as the circles, a triangle. However, when you have 4 spheres, you can use this 3rd dimension. And this creates a tetrahedral arrangement. When you try to pack 4 spheres together as close as possible, it will create a tetrahedral arrangement. Now, once you get up to 6 spheres, there's a different arrangement that's not based on the tetrahedron, but is based on the octahedron. Here, you essentially have 4 spheres in a square instead of a triangle. You put 1 sphere on top and 1 sphere on bottom. And this is the optimal packing of 6 spheres. Now, this can be approximated, the spherical packing optimization can be approximated by joining balloons. And essentially, when you join the balloon, you tie 2 balloons together, there's a force to pull the balloons to the center point. However, balloons want to avoid one another. If you push them together, they'll push back out. So they want to be in a low energy configuration. They won't naturally push themselves together. They'll try to naturally be as far away from each other as possible, still with the boundary condition that they're tied in the middle. When you have 2 balloons tied, they'll create this linear formation. 3 balloons tied together will create this triangle formation. 4 of these equally sized balloons together will create this tetrahedron, the same as the spheres. And 6 balloons tied together will create the octahedron, as we see above. Now, there's some interesting connections between this spherical packing optimization and molecular geometry. And this is looking at the geometry between multiple pairs of atoms. They're often linked through electron bonds. So if 3 atoms are linked like carbon dioxide, there's a carbon in the middle and 2 oxygens. Now, there's 2 electron bonds bonding the oxygen, one oxygen to the carbon and the other oxygen to the carbon. These covalent electron bonds will try to avoid one another because they're electrically charged. They don't want to be near each other, similar to the balloons wouldn't naturally be near each other. And this creates a linear orientation of the geometry of the molecule. Now, if there's 3 electron pairs, they would try to avoid each other and form in this trigonal shape. 4 electron pairs would form into a tetrahedral shape, and this is seen in the molecular geometry of methane, a carbon atom and 4 hydrogen. 5 electron pairs creates this trigonal bipyramid, essentially a triangle in the center and 1 bond on top and 1 bond below. 6 pairs creates the octahedron. So this is reflecting, some of this spherical packing optimization is actually reflected in different molecular geometries we see. I'll just make a side note that, sometimes there's pairs that don't have atoms bond to it, but there's some extra electron pairs. Like we see this in H2O, and this can create a bent shape. So there's lots of other kind of different variations, like bent shapes when there's extra electrons, but they're not bound to other atoms, and other kind of variations. But it's often based in terms of optimizing packing. And this is just a natural form of geometry of if negatively charged electrons are in the same space and they're trying to avoid each other, they'll naturally create these shapes. Spherical packing also comes about in biology. So one example is how cells split and grow. So, cells aren't up perfectly spherical, but they're often closely spherical. And so one cell would just be in a one cell arrangement. Two cells often here in a two cell arrangement. Four cells would often create a tetrahedral arrangement. I'll just make a note that sometimes these cells are observed on a square arrangement. But actually, medical studies have shown that embryos with a tetrahedral arrangement have a higher likelihood to survive. So maybe there's a connection here between more optimal geometry and a higher likelihood that, the entire cell bodies would last and not disperse. 8 cells often create this skewed cube. A skewed cube is essentially a square on the bottom, a square on the top, but the square on the top is turned 1/8 of a turn. And this is a little bit more efficient packing than just a cube. And then more and more cells replicate, and they often create this spherical shell. And this basically separates the outside cells, like the skin, from the middle cells, like muscles and tissue, and the inside cells, like the digestive tract. And so spherical packing and geometry is essential to how the embryo grows and forms into various animals seen in nature. Spherical packing can also be seen in different seed pods in biology. So you often see 3-fold, 4-fold, 5-fold in different like eucalyptus seed pods and other seed pods. And there's often like this even dodecahedral symmetry seen. You can see this example here where it's near pentagon arrangements. Now, berries often have approximately spherical packing. They're often not perfect because each little sphere in this berry is not perfectly spherical. Some may be bigger than others. It might be squished, by an animal, and there might be more availability, sunlight, nutrients. So a lot of variations, but oftentimes these packings play a role in this macroscopic biological morphology. You can also see packing in various flowers where there's near spherical flowers, and as they grow, they'll be near each other, and so it often just creates this spherical packing. There's also icosahedral-based packing seen in biology. One example is the virus. And viruses use a number of methods to protect their RNA material. And they use various spirals sometimes, but another type of pattern they use is actually based on icosahedron. And these are various proteins that come together and they interlock to create a near approximate icosahedral symmetry. And that helps protect the material. So when the virus goes from different host to host, the RNA material inside of it is protected. Radiolarians are another interesting single cell organisms, but they develop a skeleton around them. And oftentimes these skeletons are spherically symmetrical and even based on the icosahedron and others. Here are some images drawn from various types of radiolarians. There's a huge amount of variation between all these radiolarian shapes, and it's really interesting geometry seen in there. Spherical packings can also be used in terms of architecture. One example is geodesic domes. You can create domes and even buildings, larger buildings with domes. And this is efficient for a lot of means. One example is that, as we said earlier, the sphere has the largest volume for the smallest surface area. So if you want to minimize heat transfer, maximize insulation, using a dome-like shape is a very efficient structure because it's enclosing a very large volume with this a small amount of boundary. So if you add extra insulation to that, you can make sure the inside volume stays at a given temperature. Additionally, a lot of the angles and the lengths of the edge lengths repeat in these geodesic domes. So they're fairly easy to construct because instead of having all these various pieces with various lengths, you just repeat the same edge length, maybe one or two edge lengths, maybe one or two angles, and you can create this whole spherical dome. Buckminster Fuller was really into geodesic domes, and this is one of the solutions he was thinking about in terms of a design science revolution, about designing with nature, within nature in a more sustainable and efficient way. So I want to talk a little bit about lattice structures, three-dimensional lattices. We talked some about two-dimensional tilings, and a three-dimensional tiling can be thought about as a lattice. One of the most simplest type is a cube. You can just stack cubes next to each other, left, right, up, down, back, forth, and fill an entire volume. This is just showing one element. Another type of lattice is to have what is called a body-centric cubic. This has the vertexes of a cube as well as another node in the center of the cube. And this can now be stacked in a similar way. Another really efficient type of packing is called the closed cubic packing. This essentially has all the vertexes of a cube and also vertexes on the center of the face of each cube, essentially a cube and an octahedron. Now, these kind of packings describe many of the crystal symmetries seen in nature. So a lot of these crystal symmetries, or crystals, are essentially molecules that organize into these three-dimensional lattices. They're often based on the cube, the body-centric cube, the closed cubic packing. Now, a lot of times the cube may be shear one way or it may be twisted, or there could be other variations that create various crystallography categories. But these packings provide a lot of the foundations of almost every type of crystal seen. Now, there are some other exceptions that we'll talk about soon, but just most of them are based on this cubic shape. So wanted to go more in depth on that closed cubic packing. Another way that it could be thought about is in terms of the shape, the cubooctahedron. And this is essentially taking a cube and truncating the edge points. So truncating is like chopping off. So if you have a cube and you kind of chop off each of the vertex ends, then it'll create a shape with squares and triangles. Similarly, with the octahedron, if you truncate it, then you can also create the cubooctahedron. Now, what's really interesting about this shape is if there's one sphere in the middle, 12 spheres can be shaped around it. Now, each of these elements of the cubooctahedron can now be stacked together in a lattice similar to a cube. But this is the most efficient packing of spheres in a volume. So we saw earlier the triangle, or similar to a hexagon with the circle filled in the middle, creates the most efficient packing of circles on a plane. Well, the most efficient packings of spheres in a three-dimensional volume is this closed cubic lattice, which is also made with this cubooctahedron elements. So those are equivalent. This is just taking a different slice of it, essentially. Now, wanted to go into some of these lattice structures we see. So one really common crystal that we see every day is salt. And this uses this closed cubic packing lattice. Now, this has the elements of sodium and chloride, and these have different radius because the electron clouds effectively are different sizes. And when you pack them together, it creates this closed cubic lattice. Diamond is a very, very strong crystal made with carbon atoms. And this is an interesting type of lattice. It's called a diamond cubic lattice. Essentially, each vertex has a tetrahedron, so 4 other carbon atoms coming out. And these bonds are extremely strong due to the geometry of the carbon, the amount of electrons it has. And this can also, we talked about how a star tetrahedron can fit inside of a cube. So this is essentially half of a cubic lattice, right? If you take the tetrahedron with a point in the middle as well, the body-centric, but only take half of them, then you would get this diamond cubic lattice. Ice is another type of crystal commonly seen, and this forms in these like hexagonal-like rings. So wanted to overview some of these more lattice structures. So there's these microscopic geometries, but they also create the macroscopic shapes. So we see here this calcite crystal forms in a near cubic shape. This fluoride crystal forms in a near octahedral geometry. And the pyrite crystal forms in various cubes, as well as like similar to dodecahedrons. And like I said earlier, 5 cubes can also define a dodecahedron. So if there's different cubic lattices, there are different skews to one another. Sometimes it would create these near dodecahedral shapes. Now, there are also aperiodic crystals. Now, this aperiodic crystals were thought to not exist because only that cubic and regular periodic crystals were thought to exist. But it turns out that some crystals, if you shine light through them and you see the diffraction pattern creates this 5-fold symmetry. And like we said earlier, pentagons and 5-fold don't neatly stack together. So this is showing that there's some aperiodic nature of it. And it creates similar patterns that we see as this aperiodic Penrose tile. Now, this is a 2-dimensional slice, but this just gives you a sense of some of the symmetries, some of the icosahedral symmetries, the aperiodic symmetries seen in the diffraction patterns of some of these aperiodic crystals. Now, this isn't a crystal, but it's also an interesting type of molecule that has an icosahedral symmetry, and this is the buckyball. And essentially, the buckyball is made with 60 carbon atoms, and it forms a shape similar to a dodecahedron, but with the truncated in such a way that it's made with hexagons and pentagons, kind of like a soccer ball. And so this goes to show that, not all of these like molecules are just based on cubic lattices. There's also dodecahedral, there's also aperiodic lattices. So we went from 2-dimensional to 3-dimensional. Now we're going to go from 3-dimensional to 4-dimensional. The circle has a 3-dimensional analogy or analog of the sphere. Now, if you take the sphere and you go to 4 dimensions, it's the hypersphere. And what's really interesting about a hypersphere is that the boundary of a sphere can be characterized by a plane. However, the boundary, or a 2-dimensional boundary, the boundary of a hypersphere can be characterized by a 3-dimensional boundary. So in a hypersphere, for example, you can go straight in a 3-dimensional space, but that 3-dimensional space can be warped around in 4 dimensions, so that line can go back to itself. So it's a really interesting, kind of like warps your brain, where basically volumes can be warped around one another in a 4th dimension. So we saw the regular polygons in 2 dimensions. We saw the regular 3D polyhedron. Polytopes extend this notion to n dimension. And so we can see the 4-dimensional regular polytopes. And the elements of this is made with the regular Platonic solids. So the regular solids are the elements of these 4-dimensional polytopes. So the 5 cell is created with 5 tetrahedrons. Now these are kind of warped around each other, but it creates this object called the 5 cell. The 8 cell is 8 cubes stacked together, warped around in one another. The 16 cell is 16 octahedron, warped around in one another. The 120 cell is 120 dodecahedron. The 600 cell is 600 icosahedron. Now, what's really interesting, there's this 6th solid, the 24 cell, and there's no direct analog in 3D. This is a new type of symmetry not seen in 3 dimensions. So the 24 cell has a lot of interesting properties. It's also the most efficient lattice packing in 4 dimensions. So we saw that triangular lattice was the most efficient in 2-dimensional. The cube to octahedron, the closed cubic packing, those are equivalent. We saw those were the most efficient packing of spheres in 3 dimensions. Now, when it comes to 4 dimensions, the most efficient packing of the hyperspheres is using the 24 cell. Now, these higher dimensions may seem really abstract and connected to nothing to do with nature, but there's been some theoretical physics that uses a lot of these higher dimensions. One of this is the notion of a Kaluza-Klein model. And this was kind of an early model. One could even think about it as maybe a very early type of string theory. But the notion of it is that maybe there's some hidden dimension that we can't see. That if we zoom out, we see a path, but if we zoom in, perhaps this is really a cylinder. And that this could maybe describe electron spin and other types of aspects we see. So this was an early attempt to try to unify gravity with other electromagnetic forces. And the notion of this is that maybe there's some hidden higher dimensions that at the very small scale that look like a path, but maybe it's actually tracing out a cylinder. So the Calabi-Yau manifold is another more commonly used manifold when it comes to string theory. And string theory is basically an attempt to unify gravity with the other forces, the electromagnetic forces, the strong and weak nuclear forces. And this has a similar idea. Perhaps, at the macro scale, we see 3 dimensions, but when we zoom in, there may be some hidden dimensions that are folded up. And the various symmetries of this hidden dimension, maybe that describes all the various particles we see, all the various subatomic particles, maybe different reflections of these different symmetries. So string theory tries to work out some of these various things. There isn't experimental proof of string theory right now, but these are some interesting theoretical physics that uses higher dimensions. Also, higher dimensions can be used in crystallography when looking at the diffraction patterns, especially these aperiodic diffraction patterns. You can use higher dimensional solids to try to understand the symmetry seen in those diffraction patterns. So one of the most generalized ways to think about symmetry is to think in terms of groups. And there's this whole field called group theory. So we won't have time to get into all the nuances, all the really cool things, but wanted to highlight some of the really interesting aspects about groups. Now, a group is representing every symmetrical transformation of a given object. So let's imagine this equilateral triangle here. Now, the vertexes of this equilateral triangle has been labeled A, B, and C, just so we can keep track of it. But the object itself is not labeled. So the identity is perhaps a mapping is just keeping the triangle as it is. Or maybe another mapping is to rotate it 360 degrees. But all these identity mappings will keep the triangle as it originally was, where A, B, and C are in the same locations. Now, another mapping symmetry of a triangle could be to rotate it to the right 120 degrees. And we see here that the vertexes have changed. Another one would be to rotate to the left 120 degrees. Now, you could rotate 360 and 120, but that would give you the same thing. So that's thought about as the same type of symmetry. You can also flip the triangle along the A-axis, the B-axis, or the C-axis. Now, this represents all the rotational and reflection symmetries of a triangle. There are no more. So this is the group of the triangle. This is all the symmetrical mappings of a triangle. So the group, just to summarize again, is all the symmetrical mappings of a given object. And groups have other mathematical structures. They're very interesting to study, and they play a key role in physics, as we'll see. One of the most useful groups in physics is called the special orthogonal groups. So this is represented here SO parentheses 2. And this is a special orthogonal group with 2 real numbers, so X and Y. So what this represents is all the rotation symmetries of 2 real numbers. Now, what this essentially is basically all the rotations of a plane. And this can be thought about as tracing a circle. So there's only one dimension, there's only one angle. Now, we talked about earlier, the group is all symmetrical mapping. So this is an infinite list, right? Maybe 1 degree, 2 degree, 3 degree, and so on and so on. But this represents every continuous rotation of a plane, X and Y. And now, what's really interesting, we saw earlier with the polygons, like the triangle, square, pentagon, those can all be thought about as subgroups of SO2, of the special orthogonal 2 real numbers. Those are just certain, they only have certain rotations like 2-fold, 3-fold, 4-fold, but SO2 represents a continuous rotation. So if something is like a circle can be continuously rotated, that would have this SO2 symmetry. Now, what it traces out is something called a one sphere. And a one sphere is essentially a circle. It means there's a one-dimensional boundary, and this creates a circle. Now, SO3 is looking at all the rotations of 3 real numbers, X, Y, and Z. Now, X, Y, and Z, it can be rotated along each of the axes. So the size of this group, there's 3 angles: the angle along X, the angle along Y, the angle along Z. And this can be thought about, let's say there's a moment of inertia, right? You're trying to understand the angular momentum of an object. It might be easier to rotate one way than the other way. Well, this kind of symmetry is useful to understand these kind of things. Now, interestingly, you would need a 3-sphere. Now, a 3-sphere is basically a hypersphere because there's a 3-dimensional boundary to the sphere. So you don't need just a 2-sphere, which is like a normal sphere, a sphere with a 2-dimensional boundary. You would actually need a 3-sphere. You would need a hypersphere to capture all the various sizes of how this can transform. So it's kind of interesting that the 3-sphere doesn't equal, what you may expect like a 2-sphere because it's 3 dimensions. But this is for the special orthogonal group with 3 real numbers. Now, the unitary groups are basically a similar kind of way of approaching it, but now using complex numbers. So complex numbers have a real component and an imaginary component. And this imaginary component is reflected with the symbol I. And basically, I follows the rule that I squared equals -1. And this is really interesting to calculate various things, even in physics and also in pure mathematics. So one complex number can be reflected with the real component A and an imaginary component BI. So U1, the group U1, is all the rotations of one complex number. Now you can see that this just rotates, there's one angle, and this is basically the same as SO2, right? It can be thought of almost as equivalent as a real number X, a real number Y, except you're changing Y to this imaginary number BI. And this traces out a 1-sphere circle. Another one, SU2, the special unitary group on 2 imaginary numbers, has 2 imaginary numbers. So one is A, B times this imaginary, another one is C, D times this imaginary. And basically when you calculate it, you see that there are 3 types of angular ways that this 2 complex numbers can be rotated. And this traces out a 3-sphere, very similar to the SO3. Now you can extend this further. So SU3, the special unitary group on 3 complex numbers, has 3 complex numbers. Now there's 8 types of angular rotations, and the geometry that would encapsulate all the various rotations of these 3 complex numbers is this kind of complex thing. It's basically like a 3-sphere, so this hypersphere, but it's a fiber bundle, which is part of like a hop vibration over a 5-sphere. So these kind of fibers of a 3-sphere traced over a 5-sphere. We won't get into all these various geometric spaces which can allow all these groups, but what's really key to note is that groups, like we said earlier, represent all the symmetrical transformations of an object. The special orthogonal groups are all about rotations of real numbers, about how can any rotations in a dimensional space be made. The unitary groups and special unitary groups are all about rotations, but now using complex numbers. Now, these unitary groups are essential parts of physics. Now, we saw earlier in a previous chapter that symmetries like the same experiment performed at different locations, different translation locations, leads to, combined with the principle of least action through Noether's theorem, leads to the conservation of linear momentum. The symmetry of rotation that, physics shouldn't care what rotation my coordinate system is in, combined with the principle of least action, would lead to the conservation of angular momentum. And the symmetry of time, that experiments should occur with the same conditions of what time they're performed in, should lead to the conservation of energy. So basically, Noether's theorem showed that within a continuous differential field, basically a continuous field and differential is something that changes over time, combined with the principle of least action, that would lead to the conservation laws. However, those were extrinsic symmetries. There's also intrinsic symmetries. So for example, the polarization of light or electron spin, is it up or down? Now, complex numbers are often used in quantum mechanics to describe, is an electron up or is an electron down? And this, it's not like all electrons are facing up in our, in the universe and all are facing down. Up electron could be this way or this way. It's only about the relative, intrinsic symmetry. So what this comes about is that the electric charge uses this unitary one symmetry. So all the rotations of one complex number. So you have that symmetry combined with the principle of least action and Noether's theorem. Now this produces the conservation of electric charge. So these symmetries are essential to creating the conservation forces. The special unitary group we saw earlier, basically the rotations of two complex numbers, leads to the conservation of weak isospin, which is essentially the weak nuclear force. And that SU3 that we just saw earlier, all the rotations of three complex numbers, leads to the conservation of color charge, which is the strong nuclear force. This is about like how gluons, which are subatomic particles inside protons and neutrons, behave. So a lot of times when symmetry is thought about in terms of deep physics, this is how it's thought about. That there's these deep, deep symmetries. It's not just saying, oh, a crystal is a given shape, a snowflake is a different shape. Regardless of all the shapes possible, of given electric charges, there's this deep symmetry of this unitary group, all the rotations of a complex number. Now, combine that with the principle of least action, Noether's theorem, now you have the conservation of electric charge. These are very fundamental aspects used in physics. The SU2 group, the weak isospin, the weak force, SU3, the strong force. So this is oftentimes, regardless of how it's shaped or whatever, there's these deep symmetries involved, these deep intrinsic symmetries, in addition to those extrinsic symmetries leading to the conservation of momentum, linear and angular, as well as the conservation of energy. So, hope you enjoyed this lecture on symmetry. Next up is fractals. So if you want to get a free PDF of the book, go to davidsugar.com/book. Also, if you want the paperback, go to amazon.com. Thanks for tuning in and see you next time.